Hello, today I will be presenting the sickness absence analysis I conducted at Medway Foundation Trust Hospital. While seasonal trends are easy to spot in the data, sickness rates can also be seen to differ between service areas, and my focus is going to be on whether this difference is statistically significant or could just be down to random chance. We all intuitively expect there to be some variation between, say, infectious disease wards and clerical departments, but I wanted to do this study to quantify the variance using the scientific method and formal statistical testing. The operational issue driving this research is the fluctuating workload and cost pressures caused by sickness. We know that staff being off sick, often at short notice, creates patient safety risks and forces us to use costly agency staff. But without statistical testing, we cannot know exactly where to target our resources. My goal is to provide evidence that can support workforce planning to ensure safe staffing levels while also reducing the use of agency cover. We also know that some wards have protocols encouraging staff to stay home at the earliest sign of a sniffle to avoid risking passing on infections to our vulnerable patients. Operationally, this is clinically sensible, but it may also contribute to more short-term sicknesses in those areas. Part of this analysis explores whether such practices are visible in the data. By formally analysing sickness rates across all our service areas, this study provides a data-driven foundation to identify exactly which areas are driving these pressures, rather than relying on hunches or anecdotes. To evaluate this question, I framed it as a testable hypothesis. The null hypothesis is there is no significant difference in sickness rates between hospital service areas, and the alternative hypothesis is there is a significant difference. This is a classic between subjects comparative study. Our independent variable is a categorical one, the service area category, which I have divided into 4 groups, and our dependent variable is the sickness ratio, which is a continuous numeric metric. By testing whether the sickness ratio differs between these groups, we can provide evidence that directly informs workforce planning decisions. The conclusion I came to was that sickness rates do vary significantly across service areas. High dependency units consistently have the largest sickness ratios. They are also shown to have the greatest number of sick days per person, and within these units, acute medics was found to be a significant outlier with a sickness ratio of 90%. I also observed an unexpected small peak anomaly around October. Workshop discussions helped interpret this, but more about that later. The rest of this presentation walks us through the statistical approach that demonstrates why this conclusion is robust, and then goes on to show why these findings matter and what can be done with this information. So the data I used covers all sickness events recorded in ESR, our electronic staff records database, between September 24 and August 25. In total, it represents over 5,000 staff across 198 service areas, so it's a comprehensive view of the trust. To make meaningful comparisons, I grouped the service areas into 4 subcategories: patient-facing high dependency units, HDU, such as intensive care and maternity; patient-facing low dependency units, LDU, such as orthopedics and day cases; back office but frontline roles like portering and housekeeping; and back office admin roles like home workers or desk-based staff. The key metric analysed is the sickness ratio, calculated by dividing the number of sickness events by the staff complement in each area. This normalisation means a ward of 12 can be directly comparable to one of 80, reflecting the proportion of staff affected rather than raw counts. Ensuring fairness across groups allows us to test whether sickness rates differ significantly between categories independent of team size. This approach matters because it provides objective evidence that can guide workforce planning and targeted support, such as cross-skilling to reduce the use of agency cover. It also helps identify outlier areas that require operational attention. For example, if one area consistently shows extreme sickness ratios, that area could become a priority for quick-win interventions. Before running formal tests, I looked at the descriptive statistics to understand the data's shape and decide which test to run, as suggested in Statistics for Dummies by Rumsey 2016. The histograms clearly suggested that sickness rates are not equal. Mean sickness rates varied noticeably between groups, HDU having the highest and also the largest variance, hinting at a possible difference worth testing. Looking at the distribution, skewness and kurtosis showed that all groups were broadly unimodal, meaning a single peak, and were all approximately normal. HDU and Frontline showed the strongest right skews around 2.7. LDU and Admin were both relatively balanced and broadly symmetrical. For kurtosis values, HDU had a sharper peak and a heavier tail, indicating more extreme sickness ratios. Frontline appeared slightly flatter but also had a tail. LDU and Admin were both close to normal. These descriptive statistics show me that we have one categorical independent variable and one continuous dependent variable. The groups are approximately normal and the data is independent of each other. The sample sizes range from 12 to 90 data points. Therefore, as outlined in Stratology's Decision Tree Guide by Palomares Caracosa 2024, I can use a two-tailed one-way ANOVA. This is a parametric test designed to compare the means of multiple independent groups and asks, is the difference between them large enough to be significant? If so, we can reject the null hypothesis of no difference and accept the alternative that sickness rates do differ between service areas. But before using ANOVA, it's important to check the assumptions that underpin it. Normality. I assessed this using the skewness and kurtosis values. All groups were approximately normal, with mild right skews in HDU and Frontline. ANOVA is generally tolerant of moderate departures from normality, so this is acceptable. Independence. Each observation represented a distinct service area, so duplicate long-term sickness records were removed, so therefore this assumption is also satisfied. Homogeneity of variance. This is the assumption that the spread of sickness ratios is equal across groups. When I compared sample variances, HDU stood out with a variance of 0.04 compared to 0.01 for LDU and Frontline and 0 for Admin. This imbalance suggests a possible violation. To formally test for unbalanced variance, I ran Levine's test. The result was borderline non-significant, with a p-value just above 0.06, meaning although the difference in variance is noticeable, it does not cross the threshold of 0.05 for statistical significance. In practice, ANOVA is considered robust to mild variance inequality, especially when group sizes are reasonably balanced. Still, the elevated variance in HDU means results should be interpreted with caution. If the variance gap had been larger, or if Levine's test had been significant, alternate analysis could have been the non-parametric Kushkal-Wallis test or Welch's ANOVA, which adjusts the degrees of freedom to account for an unequal variance. Including this diagnostic strengthens confidence that the differences we observe in the data are genuine rather than artifacts of variance imbalance. Once the assumptions were checked, I ran the ANOVA itself. The results showed a very clear statistical finding. The F statistic was 9.79 and much larger than the F critical value of 2.65, with degrees of freedom of 3 between groups and 194 within groups. This confirmed that variance between service areas is far greater than those within them. The p-value was far below the threshold of 0.05, showing the probability these differences occurred by chance is vanishingly small. The effect size eta squared was substantial, indicating that service area explains a meaningful proportion of variance in sickness ratios. So we can confidently reject the null hypothesis and conclude that sickness rates do differ significantly between service areas. Operationally, this is important because it confirms that the highest rates seen in HDU and the lower rates in Admin are not just anecdotal impressions or random fluctuations, they are statistically significant differences. This evidence allows us to move forward with targeted interventions, for example, amending sickness reporting protocols or setting up cross-skilling in areas of greatest burden. Page 1 of this report shows the box plot comparing sickness ratio across the groups. HDU stood out immediately. Its interquartile range spans from 20 to 35%, with a mean at 29 but a median at 21%, which tells us that the mean average is being pulled up by extreme values, a classic sign of the positive skew we identified earlier. The HDU spread is also much wider, with a standard deviation of 0.2 and a sample variance of 0.04, compared to just 0.01 in LDU and Frontline and 0 in Admin. The greater spread means HDU is not only higher on average, but also more unpredictable, which makes managing staff rotas that much harder. Interestingly, while HDU has the highest mean, Frontline actually had the highest kurtosis, meaning its distribution had a heavier tail. So while HDU is consistently elevated, frontline is more volatile. The sample sizes also vary between 12 for HDU and 90 for LDU. This imbalance means a single area in HDU can exert more influence than a single area in other groups. Taken together, the box plot reinforces what ANOVA showed. HDU has high sickness ratios and greater variability, whereas frontline is more volatile than expected, and admin remains the most stable. These patterns help explain why some areas are harder to rota staff safely and why targeted interventions are needed. ANOVA confirmed that at least one mean was different, but it doesn't tell us which group or groups it belongs to. To answer that, I run a 2-key HSD post hoc test. This uses the mean square within value of 0.00834, the harmonic mean sample size of 27.6, and a critical Q value of 1.972, giving a resulting 2-key threshold of 0.034. So, group mean differences only reach significance if they are larger than 0.034. And the results were very clear. All the HDU differences were in the region of 0.1 to 0.15, around 4 times the 2-key threshold, confirming that HDU was significantly higher than every other group. LDU and frontline were almost identical to each other, and both were significantly higher than admin. This pattern matches operational intuition that staff in HDU not only face greater infection risk, but as they are encouraged to stay home with a sniffle, this drives them to have the highest sickness rates than any other area. Meanwhile, admin staff who are less exposed to sick patients and who possibly underreport sickness due to working from home have the lowest sickness rates. What's important here is that the 2-key test validates the differences statistically, not just anecdotally. So the post hoc analysis gives us a clear hierarchy, HDU at the top, LDU and frontline in the middle, and admin at the bottom. That hierarchy is crucial for decision makers. It shows exactly where interventions will have the greatest impact, HDU. It also might hint at underreporting in admin areas, which could indicate a culture of home workers not reporting while sick, which could eventually lead to burnout, another thing to watch out for. Because the HDU category showed both higher averages and greater variance, I then checked for outliers and whether any single area was exerting a disproportionate influence. To do this, I used Cook's distance, an influence statistic test measuring the impact of each data point on the overall results. The analysis highlighted one clear outlier, acute medics. This area recorded a sickness ratio of 90%, and its Cook's distance value exceeded the conventional threshold of 1, confirming statistically that it exerts a strong leverage on the model and pulls the HDU mean upwards. However, this result doesn't invalidate the ANOVA findings, as the difference between groups remains significant even without this area, but it does identify acute medics as a priority area for intervention. Operationally, it's a double burden. The influence of acute medics distorts the overall picture of HDU, and its extreme sickness ratio drives agency spend higher. By flagging it explicitly, the analysis points to where a targeted review could yield the greatest impact. After this, I also wanted to test whether sickness burden simply scales with how big a service area is. In other words, do larger teams have different sickness ratios? To check this, I ran a simple regression analysis, plotting sickness ratio against staff count. The result was striking. The regression line was almost flat, with an R-squared value of just 0.0042. This means that less than 0.5% of the variation in sickness burden can be explained by team size, showing it is statistically negligible. There is no meaningful relationship. So the conclusion is clear. Sickness rates are not determined by how many staff an area has, but by the nature of the work itself. Acute medics carry high risk because of their environment, not because they are larger than any other HDU area. Next, I assessed the quality of the data set and the potential biases that might influence the framework using the government's Data Quality Framework, GDS 2025. For quality, accuracy was strong as sickness data is auto-logged in ESR, reducing manual error. Completeness was good for sickness episodes, though secondary paperwork was less consistent. Reliability was high as ESR is the system of record, though minor variation in data entry practice is not acknowledged. Relevance was clear since sickness cover is directly tied to workforce planning, and timeliness was appropriate as a full 12-month dataset could support annualised analysis. For biases, selection bias was minimal since the full population was included, so representativeness was not a concern. Survivorship bias was also minimal as leavers are retained historically. Omitted variance bias was moderate because factors like acuity, rotor load and management styles aren't captured in ESR. Observer bias was low, though sickness classification can vary slightly between teams. One pre-mentioned cultural bias is particularly relevant though, that of the HDU sickness reporting protocol. This isn't a flaw in the data, but it is a bias in the system, one that could go to explain why they have higher sickness ratios. By acknowledging these data quality checks and biases, we strengthen confidence in the results while also recognising the operational context behind them. Even with strong DQ checks, it's important to acknowledge the limitations of the analysis. First, the metric counts sickness events rather than unique individuals. So if a person has 2 in a month, only the first is counted. Therefore, it does not measure the full burden on the individuals. Secondly, duration is not differentiated. A 1-day sickness is treated the same as 2 weeks. This simplifies the analysis, but does not measure the operational impact of longer absences. Third, variance in HDU is very high, which means a single area changing its behaviour could shift the group average greatly. And finally, some operational factors are not captured in ESR, acuity level, rotor load, management styles, and particularly the uneven sickness reporting protocols. These all influence behaviour but are not visible in the data. Despite these limitations, the findings remain statistically robust and operationally meaningful, but recognising these caveats helps ensure that decisions based on the analysis are realistic and grounded in context. In conclusion, the analysis shows that service area category is a significant predictor of sickness absences. High dependency areas have consistently higher sickness ratios, while admin areas have consistently lower. Low dependency and frontline sit in the middle, broadly similar to each other. One specific outlier, acute medics, recorded a sickness ratio of 90%, which means almost every staff member reported in sick at least once every month across the year. This group exerts a strong influence on the data, and operationally it represents a huge burden because specialist cover here is harder to source and is more expensive, thus making it a priority area for intervention. Beyond the statistics, workshop discussions with the roster team added valuable context. Colleagues explained that in acute medics, some staff struggle to secure annual leave during school holidays, and when turned down, resort to calling in sick instead, often for the full 5 days. This behaviour inflates both the frequency and the average length of absences, which not only helps explain the extreme outliers we observed, but also the unexpected small peak in October. Including this feedback demonstrates how statistical analysis combined with operational insight can highlight not only where sickness burden is highest, but also why they occur, strengthening our understanding of the data. The findings also highlight a cultural feedback loop. Staff in HDU areas are encouraged to stay home at the first sign of a sniffle to avoid risking patient safety. While clinically sensible, this drives more frequent short absences. Over time, these accumulate, triggering occupational health thresholds and forcing mandatory meetings. This creates a feedback loop of wasted management time and increased stress for staff, a cycle that compounds the sickness burden. So perhaps HDU sickness triggers should be raised to compensate. Taken together, these results provide a clear evidence base for decision makers. Targeted wellbeing support, workload reviews and cross-skill programs should be prioritised in HDU, especially acute medics. Doing so will not only improve staff wellbeing and patient safety, but also reduce reliance on costly agency cover, delivering both clinical and financial benefit. Looking ahead, there are several ways we could extend the analysis. Firstly, incorporating sickness duration could add depth and highlight the true operational impact. Secondly, repeating the analysis across multiple years as part of a broader trend analysis could test whether the peak we observed is a one-off. Finally, integrating non-ESR operational factors and qualitative feedback from workshops more systematically could strengthen the link between statistical findings and lived experience, ensuring that interventions are both evidence-based and culturally sensitive. Together, these extensions could build a richer picture and provide even stronger guidance for workforce planning. And lastly, I wanted to say that I have tailored this presentation to my audience. Here, the focus is on decimal place precision and statistical detail, because that's what my senior managers expect to see. Were I presenting to a more general audience, I would adapt the style using more charts and infographics and make the findings visually intuitive and simplify the language to highlight the key takeaways. I've also considered accessibility. The slides use a blue background to support disabled compliance, particularly autism readability, and I've chosen a clear high contrast sans serif font to maximise legibility. For workshops, I would add interactive elements to build engagement, like asking colleagues to interpret a chart before revealing the statistical test. So the presentation is not only rigorous, but also adaptable and inclusive, ensuring that the findings can be communicated effectively to different audiences.